Let's say you hire a tireless researcher. They never sleep, they never take a coffee break, and they process raw data at the speed of light. Right now, that level of autonomy is a fantasy. Today's artificial intelligence is incredibly capable, but it is entirely passive. It sits idle, waiting for you to type a prompt, acting as an advanced autocomplete engine that predicts the next best word or pixel based on your direct instructions. To get a system that actually works on its own, what engineers call agentic AI, the software has to break free of that prompt and response loop. It needs to look at a massive, complex problem, break it down into dozens of smaller steps, and solve them sequentially without human intervention. You cannot just patch that in with a software update. Handling that immense, continuous cognitive load requires a physical shift in the machines we use to process information. Every computer on your desk or in a server farm relies on classical binary logic. They process information strictly as ones and zeros, taking in data and moving it through a sequence, one step at a time. Those ones and zeros are controlled by tiny switches called transistors. Engineers have shrunk these components to the atomic level to increase speed, but we're hitting a wall. We cannot make them smaller before the laws of physics interfere with their function. Now imagine an active AI simulating and verifying millions of independent choices simultaneously. Because classical processors are forced to evaluate those options sequentially, that data piles up. The software is demanding millions of calculations a second, and the hardware is forcing them to wait in a single file line. Building true autonomy on silicon chips is like putting a lawnmower engine inside a Formula One car. This brings us back to the software side of the equation. Think of agentic AI as the driver. Instead of typing a micro prompt like write a Python script, you give the driver a high-level macro goal, like find a compound that cures this specific disease. This diagram shows how the cycle operates. The agent autonomously breaks your macro goal into actionable subtasks. It writes its own code to test a hypothesis. It tests that code, identifies errors, and corrects itself, all without human input. The driver knows how to navigate the path to a discovery, but as long as it operates on classical hardware, it is trapped calculating each step at a speed far too slow to be useful. The driver relies on a different machine to function, the engine. This is quantum computing, a departure from traditional silicon. Classical bits use a rigid 1 or 0. Qubits utilize superposition, acting as a sphere of probability existing in multiple states simultaneously. It no longer evaluates problems in a single file line. A quantum computer explores millions of pathways instantly. The bottleneck is gone. Quantum hardware delivers the processing scale required to handle exponential problem-solving in real time. When you fuse these two technologies, the limitations vanish. Agentic AI acts as the navigator, providing the direction, and quantum computing supplies the raw horsepower. Consider pharmaceutical research. The AI agent proposes a complex new chemical structure to target a virus. Immediately, the quantum engine calculates the physics of that structure, twisting and locking the molecule together to see if it holds up. The system iterates, fails, learns, and corrects itself in milliseconds. Traditional silicon chips simply cannot process information at this velocity. Working together, the software and the hardware form a single entity capable of generating, testing, and refining vast ideas in the blink of an eye. We are rapidly approaching the end of human prompt engineering. Soon, these systems will formulate their own prompts. They will actively hunt through our data, searching for inefficiencies and calculating solutions to problems we haven't even realized we have yet. At a macro scale, synchronized networks of these synthetic researchers could independently monitor global logistics chains or rebalance regional power grids, identifying and optimizing connections in hours instead of years. But as these systems begin to operate autonomously at quantum speeds, a new challenge emerges. We have to ensure their independently generated goals remain strictly aligned with human safety and values. The focus has moved from building faster calculators to engineering the autonomous digital colleagues that will guide the next century of discovery.